Hello again, everyone. This is Brendan. Now that I went over kind of the methods that I used when I was experimenting with different box construction methods and explained that in the first video, I kind of wanted to go over the plots and so you kind of understand, what these things are saying. So the first thing to know is this red line here is the bare driver, and that was mounted outside of the box, right? So this is what you would actually hear from a normal driver. And then I took the microphone at the rear and at the side panel. And I did both of them because I didn't know how they might be different. The side panel is much wider, the span's wider, so it's going to be a little more flexy than the rear panel. The rear panel is opposite the baffle where the driver's firing into. Is that going to affect things? I wasn't really sure. So through all this testing, I've just taken near field measurement at both the rear panel and the side panel, and that's what those two plots are right there. Now, I worked to scale the SPL correctly. So when you see this 3 dB below, this peak 3 dB below the bare driver, it really is that loud outside of the box. Okay? So this was the first thing that really surprised me, that some of these resonances could be so high and level. And so, I think it's pretty obvious that from this that you do have to do something. Now, how far down it needs to be, we can have a debate about that. But I think there is clearly going to be problems here in a normal box. We do need to do something about it. Okay, so another thing to note, the bare driver response was, I think, 7 millisecond gated. So you have about 150 hertz cutoff. When I did the near field of the rear and the side, this is actually more like 50 milliseconds I think I use to get a lot higher resolution, especially at the lower frequencies here. But this is probably a key part. At around 250-ish, more and more of the background noise in my home starts to bleed through. And so you'll see these lines kind of go everywhere on different measurements. Just ignore that. This data is just invalid. The noise floor is too high. So we're really looking at just 250 and above. I don't think this is really a problem as far as getting good data because of the regions. And so that's probably the next good topic to get into. I look at this frequency response as having 3 regions. From about here down to 0 is a region where the stiffness of the enclosure dominates. So this is just the air pressure inside the box, flexing the walls of the box, making it be its own source of bass. And you can see that effect most clearly when you brace the box. So I should note that this box, this first box that I'm making, and I'm just checking the material of the box, this is an unbraced box and it's an unlined box. It's just a simple box. As soon as you add braces, what you see is this response right here drops down to here. Okay, so I think we can extend, although I can't be sure, but I think it's safe to say from other work that's been done, when you're in this region, this is stiffness dominated and everything's going to behave like this. You stiffen it and your SPL is going to drop down. And then we have the next region, which I'll mark from here to you know, maybe here. Now, of course, this is all dependent on the geometry of the box. Smaller box is going to shift everything up a little bit. Bigger box is going to shift everything down a little bit. And I'm going to revisit that in a second, though. This is what I call the primary panel resonance region. This is not the pressure inside the box. It is sound being transmitted through the air inside the box, but it's also sound transmitted through the panels of the box itself from the driver. And this is where you have the real problems, quite obviously. Then we kind of drop down here. I don't consider this probably all that bad, but then you got a couple more spikes there. So this, to me, is the heart of where you have real issues. They're high in SPL, and we should probably do something to solve it. Okay, and that's the low-hanging fruit. And then we have a region from about right here all the way up to our limits. And I've seen this called the mass-dominated region in the literature. And really, it just does come down to what is the thickness or mass of the material that's there and what is its own internal dampening. And you just have a steady roll-off with frequency. Okay. Anyway, so I think that covers everything I wanted to go over. Again, probably the main thing to understand is under 250 or so, maybe 200, my room starts to come in. There's 3 regions that are important in different ways. And I guess to wrap it up, so that's why I made the choices that I did. At the end of the day, I think this was the best way to A, mimic a real box, and B, get measurements that actually have something that we can relate to, right? An actual frequency response that I can relate to. And to prove it, you want to know what this sounds like? Well, it's pretty much just how it looks. You can hear the steady state white noise that's being fed into it. But what really dominates is this, and it kind of just goes, ooh. Hope that comes over on the microphone well. But you can hear this sort of mid-range tone. The box has a tone to it, and it's this, right? So I guess what I'm trying to say is this is meaningful. You do hear this, and it's a high enough level that, it's going to intrude, and this is the region that I think we need to spend the most time in. And so anyway, I hope that helps people understand why I did what I did. Clearly, there's other ways to do things. The question is, does it provide the best balance of compromises? Is it the most realistic? And is it giving me data that my little monkey brain can actually relate to? Okay, thanks guys.